Welcome to Toddcast number 52. This is just a heads up. This is where we're kind of turning a corner and things are going to get going really, really fast for the duration of this semester. And what I mean by that is not that we haven't been going fast at this point, not that we haven't covered a lot of information, but these reactions, there are just a ton of different ways to do some of these reactions, lots of different applications in both biology and chemistry. And so it's going to feel like information overloaded at certain times. Whenever that happens, always a good idea to take one or two steps back, look at the big picture, draw your large maps, whether it's spider charts, clock charts, flashcards, whatever way you learn the material, focus on picking up material. Once you're ready for that, then back to mechanisms and alternative ways of doing the same reaction. And that's probably going to be where things really pile on, is that we will talk about multiple different ways to do a reaction under different conditions: acidic, basic, neutral, lipid environment, polar, protic environment, whatever the conditions may be. And so it's learning lots of different ways to do the same thing. Okay, I want to start with redox chemistry and just revisiting what you did in general chemistry. I want to toss a mnemonic out there, and we did it earlier, but I want to reemphasize it. And that is LEO, standing for lose electrons oxidation. So if you lose electrons, cause your oxidation state to increase, becomes more positive, or if you will, less negative upon losing electrons. So lose electrons causes oxidation. LEO, and let me make it a longer version of it. LEO, the red cat, says. And if you want to go with Leo says grr, that's fine too. But Leo the red cat says grr. And I want to emphasize why I added in the red cat. It's going to have nothing to do with organic chemistry. What it will have a lot to do with is general chemistry and biochemistry / physics. What I mean by that is reduction occurs at the cathode. So this location where you gain electrons and you reduce out whatever the material is. For electrochemical cells, it's usually a cation turning into a metal. But the cathode is where reduction occurs, or the gain of electron occurs, so electrons flow to the cathode. Like I said, it's not an OChem topic, but it is so prevalent in biochem when you talk about electrophoresis, in physics when you talk about electric fields, and most often when you talk about electrochemical cells in general chemistry, that I'd like to keep it in mnemonic. So this is really a mnemonic that'll help you in gen chem, physics, biochem, and organic chemistry. So lose electrons oxidation, gain electrons reduction. We are actually going to focus on what causes the loss of an electron, or the gain of electron, the loss of a H, gain of an H, loss of an O, gain of an O, and how they correlate. And so when we say lose electrons, we're talking about two possibilities in organic chemistry / biochemistry. One, losing the electron is like losing an atom that is less electronegative, meaning if you lose a less electronegative atom that normally would be giving you an electron, when it leaves, it takes that electron with it. So electron you were given is gone, so you've lost that electron. Or gaining a more electronegative atom. So just like we saw when carbon gained bonds to O, it became oxidized because it was gaining an atom that took away its electrons through electronegativity. So lose electrons oxidation. Also, that would mean lose a less electronegative atom oxidation, gain a more electronegative atom oxidation. So I want to revisit just something we did last lecture. We talked about the extremes for carbon being an oxidation state of -4, and we had methane, +4 oxygen. We talked about going 2 at a time. So we went to -2, 0, +2, and +4. And in each case, timeout, want to keep that blue for oxidation. We gain O, we lose H, reduction, we gain H, lose O. Those become very simple to view and powerful definitions for what we're going to do in organic chemistry. So we are going to consider oxidation state from time to time, but more often than not, we're going to decide, did it gain bonds to more electronegative atoms such as oxygen, or did it gain bonds to less electronegative atoms like hydrogen, or did it lose bonds to less electronegative atom like hydrogen, or did it gain bonds to more electronegative atoms like oxygen? It's going to feel like information overload, but any of these four, and sometimes a combination here or here, can define oxidation reduction. Okay, so I'm going to get rid of everything I've written here and toss it up in this organized fashion. The reduction we're going to see as gain of bonds to H and or loss of bonds to O. They often go together. And oxidation being loss of bonds to H and or gain of bonds to O. So in doing that, when you gain a bond to H, a less electronegative atom, or lose a bond to O, a more electronegative atom, oxidation state of the carbon or the nitrogen or whatever atom we're dealing with in organic chemistry will go down. When you gain a bond to O or lose a bond to H, your oxidation state goes up, so that's oxidation. So we're going to focus primarily on the two that are in bold. That's going to be the better way to look at it. Oxidizing agents. Now, this is one of those things that if you learned in GChem, you've probably forgotten, so let me just revisit it. Oxidizing agents aren't named for what happens to them, they're named for what they cause. So oxidizing agents themselves get reduced, but in the process, they cause the other reactant. They cause something else to get oxidized. So they're named for what they cause. So oxidizing agents get reduced. I still have to say that every single time. When I say oxidation or oxidizing agents, I automatically add in the phrase get reduced. So if they're getting reduced, they have to be able to lose O's. So reduction is loss of bonds O's. So they must be rich in O to begin with, have lots of O's to give away. They're going to possibly gain H's, which means they need to be poor in H. And cases like ones we dealt with already, KMNO4, if you remember, oxidized an alkene to a diol, put two H's on there, on the carbons. O3, ozone, carried out ozonolysis, was the oxidation of an alkene, turning it into two carbonyls. MCPDA, or peroxy acid, as it's known, inserted an oxygen into an alkene that eventually led, created epoxide and eventually led to a diol as well. We're also going to now add CO3 as an oxidizing agent, a metal with oxygen, so high oxidation state metal rich in O, oxidation state metal rich in O, compound rich in O, carbon rich in O. Peroxides, we learned, are oxidizing agents as well. And these two, although this again is not going to be a focus in organic chemistry, I still want to put this in the list just so you're seeing the big picture for when you move on to other classes, or just to build on things you have learned in some of your bio classes. FAD and NADH, NAD plus, excuse me, are considered to be poor in H because NAD plus can pick up an H minus and become NADH. FAD can pick up two H's and become FADH2. Because they are poor in H, they are oxidizing agents. On the opposite end of the spectrum, reducing agents are named for what they cause. They themselves get oxidized, but they cause reduction. So reducing agents get oxidized. To get oxidized, that means they must have H's to lose, so they are rich in H to begin with. And they have to be able to gain O's in some instances, so they start out poor in O. So the dead giveaway of reducing agents will be the H's. The dead giveaway of oxidizing agents will be the oxygens. So hopefully this becomes kind of an easy pattern recognition. And just as I had mentioned earlier, NAD plus and NADH are a redox pair. NAD plus gets reduced to NADH, NADH gets oxidized to NAD plus. FAD gets reduced to FADH2, FADH2 gets oxidized back to FAD. Just like organic molecules do specific reactions, so do these. So NAD plus is usually involved in carbonyl chemistry, so formation and or reduction of a carbonyl, depending on whether it's NADH or NAD plus. FAD and FADH2, kind of like PD, if you remember that from just hop skip a few chapters earlier, deals with biological alkenes typically, not always, but typically. So FADH2 will act like H2PD, NADH will end up acting like NABH4, which we're going to learn what it does soon. You did it in lab to reduce a carbonyl, a ketone specifically, into an alcohol. And so that's going to be what this chapter is. So for now, just want to focus on the gain of H being reduction, loss of O being reduction, loss of H being oxidation, gain of O being oxidation, and that oxidizing agents get reduced and they are rich in O. Reducing agents get oxidized, they are rich in H. This is a lot of information, but you'll notice I've just repeated it over and over and over on the premise and the hope that the more I say it, the more it sort of gets programmed in. So it's not that it's hard, it's just tons of information. Okay, so how can we apply it in the question? So nice simple multiple choice question here. Which of the following are oxidizing agents except, or all the following are oxidizing agents except? So again, we want to look into the basic premise of O's. Rich in O, rich in O, rich in O. A metal with H's around, but absolutely no oxygens to be found anywhere. So rich in O and or poor in H. So as mentioned, rich in O, rich in O, rich in O, rich in O. So they are all oxidizing agents. The only one that isn't is zinc and HCl. We're going to learn that that's going to reduce carbonyls down to alkanes. Okay, so haven't learned it yet, but I should at least recognize rich in O as oxidizing agents, rich in H, and H coupled with a metal, like we learned with H2PD, H2 rhodium, H2 platinum, all the different combinations we learned will end up creating reductive states where H is gained by the carbon molecules, carbon-based molecules. Okay, big picture of things. So want to consider what exactly oxidation is. Giving you a kind of weird looking question. I'm going to learn what this group is very soon, but it's called a ketal. It's a protecting group, and I have a primary alcohol. So it ends up that primary alcohols have two H's attached in addition to OH, and for whatever reason, when something has one bond O, it becomes a target of further oxidation. So if you already have one bond O, it's easy to make a second and possibly a third. So typically, atoms that already contain bonds to oxygen will get oxidized. Ones that have no oxygen, much harder to oxidize. Certainly an alkane or sp3 carbons with just carbon and H's becomes some of the hardest ones to oxidize. But for this, we can oxidize. So let me just look and see that, yep, rich in O. So I've added something called pyridinium chlorochromate, which is what happens when you put pyridine, which gets protonated. So the H plus is going to go on pyridine. And so this is going to start out as this. This is pyridine, it's benzene, except with the nitrogen in the ring. It will become pyridinium plus chlorochromate. So Cl minus and CrO3. And what coordinates the Cr is will vary, but as long as there's no water, there's going to be no water adding to it, so only the OH can interact, and then the Cl can also coordinate potentially. Okay, what this reagent does is it oxidizes this OH. It'll take the O there, and in doing so, the when it breaks off, the H's, the electrons on this H will go there, and the electrons that were between the O and the Cr will now come back to the OC bond. Mechanism-wise, notice how I'm just talking about it and moving an arrow occasionally around. Not important for what we're going to do in this class. Maybe we'll look at it in more detail when we get into 311, but for now, just want you to know that oxidizing agents can oxidize it up. So I went from one bond to O and two bonds H's on this carbon to now two bonds O and one bond H. So I, in fact, gained a bond to O right here, and I lost this bond to H, one of them. So I lost a bond to H, and I gained a bond to O, so I've been oxidized. Point of interest, pyridine, this concoction, known sometimes as PCC for pyridinium chlorochromate, it is responsible for oxidizing up to an aldehyde. If you do not use pyridine and use water, you actually have the option of also oxidizing even further to a carboxylic acid, which will cover down the road. But for now, we'll say this is PCC, and hopefully as I keep on adding information, you'll hang on to this, but I can draw it as the reagent 03 HCl and PC pyridine, or just call it PCC for pyridinium chlorochromate. Okay, so let me erase what I've written so that what's typing in can come in. So pyridine in the absence of water forms a complex that stops the oxidation at the aldehyde, doesn't let it form the reactive species. So what this means, a geminal diol, if this species can turn into this, and so kind of like an enol can change forms from a ketone or an aldehyde, we can also turn it into what's known as a diol. Gem diol or geminal diol, because both OHs are on the same carbon, are like twins coming from the same mother. Two bonds O, this species can easily be oxidized. So now I have a carbon that's got an OH on it. It can be oxidized further, potentially. If I had no pyridine in there, it would go all the way to this functional group. Meaning it would undergo gain of a bond to O and then loss of a bond to H. So it'll gain one more bond to O. So kind of like it did here. Up here, it gained and then lost a bond to H. So same here, loss of bond to H, gain of a bond to O, going to gain a bond here, and end up as a carbene. So pyridine stops it at the aldehyde. I'm going to erase everything. So hopefully you took whatever notes you needed to. I'm going to look at the oxidation state just to make sure I know what I'm doing. So in the alcohol we start out with, I'm just going to represent R as the rest of any chain here. I'm going to go again with the primary alcohol. Primary alcohol has the OH, an H and H, and a bonded carbon. Just to revisit that way we did oxidation states last time, a carbon-carbon bond, they share electrons equally, so I give them each a 0. Carbon-hydrogen bond, carbon is more electronegative, so it gets a negative, H a positive. Carbon a negative, H a positive. O is more electronegative, so plus to carbon, negative to O. So within carbon's sphere of influence, circling around the carbon and taking consideration of its portion of each bond, it's a 0, a minus, and a plus. So overall, minus, minus, plus, and 0 add up to -1. So the oxidation state of carbon starts at -1 in this primary alcohol. It ends up, it lost the bond to H, as we mentioned. So let's just consider, let's say this H or this H. It's going to lose one of them. It only has one bond to H. It used to have 2. So that's going to be a delta of 1 electron. And then it gained a bond to O. It had 1 bond to O. Now it has 2. So that's going to be also a change of 1 electron. So let's consider the oxidation state again. Carbon, carbon, 0 and 0. Oxygen, carbon bond, so plus for carbon, minus for oxygen, plus for carbon, minus for oxygen. So I do it twice because there's a double bond. And then negative for carbon, positive for hydrogen, and that sigma bond. So I get a 0, plus, plus, and minus. Adding them up, plus, plus, and minus, add up to +1. So sure enough, when it went from -2 to, or -1, excuse me, to +1, it was in fact a loss of 2 electrons, which we already knew because losing bond to H loses an electron, gaining bond to O loses an electron. So it's oxidized by 2 electrons, which means somewhere you have to have something reduced by 2 electrons. So if it is getting oxidized, then the other reagent's getting reduced. The compound getting reduced is known as an oxidizing agent because oxidizing agents get reduced. To be an oxidizing agent, you must be poor in H, rich in O. So some of our candidates would include CO3, as we'll learn, with HCl and pyridine. We could use KMNO4, but it ends up, that goes all the way to the carboxylic acid. We could also use ones that are poor in H, as mentioned before. So we could use, if we're doing biochem, NAD+. And in the end, you'd end up with either NADH, CR in the plus 3 oxidation state. So in the first one, I did CR. So I should make note of that. that you have the reduced form, and I'm just going to put Cr in the +3 oxidation state. It could be chromic oxide, could be Cr2O3, it could be a couple different options. So it could have a chlorine involved in it. All depends on how we clean it up, but I know that went from +6 to +3, so chromium got reduced. In this case, I chose to do a biochem reagent or a bio reagent. NAD plus picks up the H. So the H it picks up is the one that left with electrons. So we mentioned that the H loses electrons. So these electrons are going to go to the NAD plus, forming NADH neutral. So H with electrons becomes H minus at NAD plus is NADH, leaving this oxygen proton to come off as a proton. So that one's this one right here. So I lose a hydride to NAD plus, and I get deprotonated, coming off an H plus. These electrons come in and form the carbonyl. There's my R, here's my H, and this now becomes 2 bonds O when those electrons go in. So again, not going to worry much about the mechanism. However, it is not unreasonable in biochem for them to say, if we labeled these two H's, so make these deuterium and this one H, or these two H's and this deuterium, to figure out where the deuterium would go, which of these two species. Okay, lots of information there. Okay, I put another reaction there, so I need to erase my stuff. So I want to bring up another example, and again, this is a bio example, but there's something called a disulfide linkage in protein chemistry between two cysteine residues. So cysteine, if you have memorized amino acids for any class, has a R group, a side chain of CH2SH. So those two SHs are able to undergo loss of H and form a disulfide linkage. So what I'm going to ask you to do is decide, is this oxidation or reduction? So we've lost two H's. Loss of hydrogen and or gain of oxygen is known as oxidation. Okay, so this is an oxidation reaction. Okay, I want to just see if I can follow that same trend. And going from C6H6O2 to C6H4O2, if you just saw a formula, loss of H, again, loss of two H's, lose hydrogens, it is oxidation. So it's just important to be able to recognize these kind of reactions in general for bio and biochemistry, and a little more specifically for how we use them in synthesis when we get into OChem. So the one we just did, although it was C6 with two O's, if I just did one with one O, here's a case where we'd go from an OH on this ring, where I have an H here and an H here, to a carbonyl. So notice I'm also losing a couple of H's, making oxidation. So it gains a bond to O, and it lost this bond to H right there. So oxidation. This reaction, I start out with 3 bonds to O and 0 C to H bonds. In the end, I end up with 1, 2. So I have 1 CO bond and now 2 CH bonds. So this terminal carbon end up losing 2 CO bonds, gaining 2 CH bonds. So 1, 2, 3, 4. It was reduced by 4 electrons. So loses bond to O, gains bond to H, reduction. This case here, we went from 2 bonds O and 2 bonds O to 1 bond O and 1 bond O. So I'm not even going to count anymore. I'm just going to notice double bonded O and double bonded O turning into single bonded O and single bonded O. Reduction. Loses bonds to O. You end up gaining along the way H there and 1 H there, even though there's also this original H. So I'm going to draw that in to be complete. But you lose bonds to O, you gain 2 H's, you've been reduced. I just realized I need to make room. So let me redraw this again. I have an H. One of the H's gets reduced, the other H gets reduced, and then the original H that was on there. You go from 2 bonds to O and a bond to H Now 3 bonds to O and no bonds to H. So you have lost a bond to H and gained a bond to O. You've been oxidized. This one's a little weird to see, and all these are going to be reactions we'll learn somewhere along the way, either this chapter or the carbonyl chapter. And what we will learn here, this one, absolutely no agents or H's are changed. 2 bonds to H, 2 bonds to H, 2 bonds to H, 2 bonds to H, and a carbonyl. Carbonyl, 2 bonds to H, 2 bonds to H, 2 bonds to H, 2 bonds to H, but it gained oxygen. So because this carbon and this carbon gained a bond to O, just like in epoxide slips into a carbon-carbon double bond, this O slips into a carbon-carbon single bond next to a carbonyl. Oxidation. This ketone with 2 bonds to O turns into a secondary alcohol with 1 bond to O. It has gained a bond to H and lost a bond to O. It has been reduced. This one's a little bit trickier. So all these, I can look straight up at what happens in terms of H's and O's. This one, I start with 1 bond to a more electronegative atom, and I now finish with 2 bonds to more electronegative atoms. So this is actually multiple steps where it probably first turned into a ketone, and then the ketone turned into an imine, a double bond N. But carbon has gone from 1 bond to a more electronegative atom, and it had an H. In the end, it has gained a bond to a more electronegative atom, and it's lost its H. So it gains bonds to more electronegative atoms, so it's been oxidized. And one last one. Count how many electronegative atoms you have on each carbon. You have 3 bonds to nitrogen, more electronegative. Now you have 3 bonds to O. I'm so sorry, I have a dust ball. So it's gone from 3 to 3. You did not gain or lose any bonds to electronegative atoms, so this is simply hydrolysis, the cleaving of a bond through excessive water. So feeling pretty good about this. Again, it's information overload at first. It certainly seems like it. But notice what we've done. We just have looked at bonds from carbon to oxygen or carbon to hydrogen and seen what's happened. So I lost a bond to that H. I gained 2 bonds to H, so I can also look at in terms of hydrogen. I gained bonds to H. This one, I lost a bond to H. Here I gained a bond to O. Here I lost this, or gained this bond to H. Lost this bond to H. No change in H's. So you can look at it in terms of H's and or O's. They're both going to work out. Okay, hopefully this is coming across as maybe not straightforward, but doable. That it all makes sense along the way. Okay, lots of information. This one gets a little bit challenging. So notice as I'm clicking along, loss of H we mentioned, gain of H, gain of H. For this one, lost an H, probably shouldn't have had that in there. This one just inserted an O, no change in H. This one gained an H, as mentioned. This one lost an H. So let me just add that in, loss of H. And the last one, nothing. Okay, so I know what the reactions look like. I can look at the reactant and I can look at the product and see how they changed. Now I want to pay a little more attention on to what reagents actually do this. So the name of this compound will actually hopefully help in what it does. Lithium aluminum hydride. And one emphasize, aluminum normally makes 3 bonds. So this 4th bond means it must carry a negative charge, which is why we need the lithium. So I need to emphasize there's a negative charge right there. Sodium borohydride, the same story. You end up needing the sodium to offset the negative. So really what this can be viewed as is a lithium plus and an H minus that's being held by an aluminum, whereas Na plus and an H minus being held to a boron. Keeping it in place will allow it to be delivered later on. So lithium hydride, sodium borohydride are 2 of my most common reducing agents. They'll be responsible for the following reaction. Reduction, reducing agents cause reduction. It's going to start with a carbonyl, a ketone in this case. And if it gets reduced, loses bonds to O, it's going to go from one bond to O, or two bonds to O to one bond, means it's going to be turned into an alcohol. So let's consider what happens with sodium borohydride. Again, has the negative on the boron. I've picked this H. I could have picked any of the four. There's nothing sacred about this one. And those electrons are going to go up to that oxygen. And in doing so, you're now going to get the BH3, the more stable form because it's neutral, although it does lack an octet. And now you're going to get a H added to these two R's and an O minus. You're not done yet. You need to protonate it. You can't really protonate it. These are all going to be hydrides and slightly negative. So we have to add in something, an alcohol, water, whatever the next reagent is, we can come and pick it up. So mild acid, an alcohol, a protonated amine, something mild will allow you to protonate it, end up with this compound. So I end up with an alcohol. In this case, ketone goes to a secondary alcohol. Notice it gained this H, so I designate it as the red H. The alkoxide that comes off, if you end up using a slightly stronger acid like a protonated amine, so instead of something with a pK around 15, we'll use one with a pK around 10. You can quench it with the protonated amine, turn it into just the neutral amine. What happens though, as we learned in from our alkene chemistry with boron, the O minus can kick in and add to the B, and so you end up with the reduced form of it, or I should say, the reduced reactivity form. I want to be careful with my word choice, but I have another H. That H can then go on to keep on doing the same thing. Okay. Just actually, before I go on too much further, for some of you in lab, you might have had trouble using sodium borohydride. We used it to reduce a ketone to an alcohol in the chromatography lab. If you contemplate what could have gone wrong, if the jar was left open and moisture got in, the top layer, so within the jar, the very surface amount of sodium borohydride will start picking up water and it'll start doing this reaction. The O's will start adding on, reduces the number of H's, so it becomes ineffective, and also becomes more subject to forms that waxy hydrate that some of you saw form. So important to make sure you keep these reagents completely dry. This one becomes less reactive. This one can actually catch fire. So lithium aluminum hydride, again, a negative on the aluminum. This hydride is going to be nucleophilic. I've changed my compound from a ketone to our group to what's known as an ester. Like, ooh, it's ester. Lots of O's there. Ooh. So ester with multiple O's, this H is going to come in and attack. So just like it did up here, it's going to attack and form this intermediate. This intermediate is going to have an H now bonded, an R, an O minus in this OR. But rather than having an alcohol come in and add a proton, we can actually have this O with its 3 lone pairs, kick electrons back in, and in doing so, dislodge my OR. So I'm still going to end up with OR, and now I'm introducing it not as an alcohol to help protonate this, but just part of the reactive species. So what's interesting here is sodium borohydride, because boron is more electronegative than aluminum, it holds on to the H's more tightly. So it can only react with ketones and aldehydes. Sodium borohydride will not work with an ester, it's not reactive enough. Aluminum being less electronegative, and the lithium being able to coordinate a negative charge a little bit better than a sodium, smaller, more like an H. Because of that combination with lithium and with aluminum being less electronegative, this can actually react with this ester, and it can form a ketone, or an aldehyde in this case, excuse me, and it can react a second time. So another reagent, so I still have 2 bonds of O. So I start with 3, I reduce it down to 2, and then I can reduce it down to even 1 more. So now I'm back to this, and this is one that's going to get protonated. So this time I've chosen to add acidic water. Again, I can use any mild acid. You don't want to use too strong an acid, it'll destroy your reagent. But if you use acidic water, once I've done the reductive step, once I'm ready to work this up, I can simply pick up a proton there. And in doing so, you end up now with, in this case, a primary alcohol. So it was a primary carbon, or a terminal carbon, I should say, within our group. Once I get rid of these 2 bonds O, I'm going to be left with this terminal carbon still, which makes it a primary alcohol. So key things to hang on to. Sodium borohydride, less reactive, only reacts with ketones and aldehydes. Whereas lithium aluminum hydride can react with pretty much any carbonyl compound, and as we'll come to learn, even potentially some imines, which we'll do in a future chapter. But this is, again, a case where we have two reactions doing the exact same thing. So as I alluded to before, what makes this challenging is we're going to learn the same basic reaction, same fundamental reaction, in this case, reduction of a carbonyl to an alcohol, but we're going to learn that different reagents will carry out under different conditions and relative reactivity. So sodium borohydride barely gets it done. Lithium hydride can get it done with anything. And so the advantage we have is if we ever have a compound that has both a ketone on it and an ester, if I use sodium borohydride, it'll only react with a ketone. I can leave the ester untouched. But if I need them both to react, then I know I need a stronger reagent. I need to use lithium aluminum hydride. That will probably be something that pops up along the way in multiple homework questions, examples in class, and then some of those scored events like quizzes and tests. Okay, which among the strongest reducing agent? Well, first let's figure out what is a reducing agent. Reducing agents must be rich in H, so this one's out. And although this is rich in H, it can be tempting, NH3 actually can't be used as a reducing agent because nitrogen is too electronegative. It won't let the H's leave as H minus. So A is gone for sure because rich in O, that's out. And then D is gone because ammonia gives off H as an H plus. It keeps the electrons because it's more electronegative. So because of that, it will not act as a reducing agent. Let me just show what I mean by that. This one can go like this and act in an acidic fashion if it's going to do anything, not in a hydride fashion, not going to deliver an H minus. Okay, it's such a weak acid that, I mean, it's so extremely weak that this isn't going to happen. So I'm not saying it will do this, it just cannot give it off as an H minus. Okay, so we're down to, again, boron and aluminum. And as mentioned, aluminum is less electronegative. Boron is more electronegative. Because of that, this one will only react with aldehyde ketones. That can only give it to something that really wants it, whereas this one can give it to anything. So because of resonance, the delta plus on the carbon of an ester isn't quite as much as it is in a ketone. So the one with the bigger delta plus, this one can react with. The one with the big or small delta plus, lithium hydride can react with. So the strongest reducing agent, the one that can react with anything, is the one that's holding on to the H minus least tightly. So we can donate this one a lot, this one just a little. Hopefully that question makes sense. There's a lot to it. So lithium hydride is a stronger reducing agent than NaBH4, making the best answer B is in beautiful. This was a lot of information, and I think this is one of those, hopefully you took lots of notes on it, and you can hope, or I hope that you keep those notes readily available when you start going through some of the future questions, and see if you can just use it to see a simplified view. Look for gain and loss of H's, gain and loss of O's, and then reagents that can provide H's and O's. So that pretty much covers it. That is it for this podcast, and I will see you at the next one. So, and apparently we'll be doing reduction of carbonyls to form alcohols. But see you at the next podcast.